Hi everyone. I apologize for having to do lecture this way, but seriously, the internet was completely horrendous this morning. Couldn't get the web pages to load at all. I'm guessing Zoom video just was not going to happen, and we tried 3 different devices at home and nothing was working. So hopefully I will be able to get this uploaded sometime today so that you can watch it. I think my email went through to all of you. I hope it did, because otherwise you're sitting here. Well, actually, we started recording this at 8:40, so in about 20 minutes you'll be sitting there wondering why I haven't started a Zoom meeting. So anyway, I hope you got my email. I apologize again. I'm serious. I'm trying hard to find a solution. Trust me, I don't know what the solution is, but I'm trying hard to find one. I will keep you updated. All right, so let's talk about eigenvalues and eigenvectors today. The whole concept of this idea is to try to replace matrix multiplication with scalar multiplication. And again, I mentioned this in the video that I asked you to watch for this material, but the whole reason why we even care about doing such a thing is that if I can replace a matrix multiplication with a scalar multiplication, I've reduced the number of computations I actually have to do to be able to do the product of the matrix times the vector. So, and it also, some long-term, what we refer to as discrete dynamical systems you can calculate what happens at any given time step by doing matrix multiplication. And if you can replace that with scalar multiplication, then you can do things like limits and see what happens over time to the system. So you see this with, like I said, discrete dynamical systems, sometimes with population modeling, sometimes with financial forecasting and those kinds of things. You may have heard of Markov chains or Markov processes, and this is another way that you can analyze long-term behavior of these types of processes if you're able to do limits. Now we're not going to be doing those kinds of things in here. We're not going to get anything that is that complex. But I just want to tell you why we care about doing such things. And if you take differential equations, there are methods of solving systems of linear differential equations where you also do what are referred to as eigenvalue and eigenvector methods for that. So anyway, I just wanted to give you a little bit of an idea of why we even care about such things, because sometimes it's hard to understand why we even worry about it. And there are lots of applications to this that you will, if you take those kinds of classes, you will be worried about these kinds of things. So anyway, so the whole idea again of this is to be able to replace matrix multiplication with scalar multiplication. So we call a non-zero vector an eigenvector if, let me change that to black, if there exists some scalar lambda such that when I take A times V, we get the lambda times the V. So I can replace the matrix multiplication of A with V with the scalar multiplication with lambda with V. So that scalar lambda that we have is called an eigenvalue of A. And then the vector V is an eigenvector of A associated with lambda. All right, so let's look at an example here to see what we're talking about with these particular numbers or these particular ideas. And I thought maybe it would help with some actual numbers here. Okay, so got the matrix 4, 0, 1, negative 2, 1, 0, negative 2, 0, 1, and these 3 vectors. All right, so to illustrate what's going on here, let's take A times V1 first. So I'll take the 4, 0, 1, negative 2, 1, 0, negative 2, 0, 1, and multiply it by the vector 0, 1, 0. Notice in the first case, when we do the multiplication, we get 0. Take the first row times the column. In the second case, we get 1. And in the third case, we get 0. So notice that this is the same thing as 1 times V1. So V1 was a non-zero vector. I can replace the matrix multiplication with the scalar times the vector. So we see that V1 is an eigenvector of A associated with the eigenvalue one. Okay. Because again, it's just the scalar multiple of v1. It just happens to be 1 times v1 here. All right. Let's do the same thing with v2. All right, so same matrix. And then we'll multiply by -1, 2, 2 in this case. What do we get when we multiply? We get -4 plus 2, so we get 2 here. We get 2 plus 2 plus 0, we get 4 here. And we get 2 plus 0 plus 2, we get 4 here. I get -2 in that first component. My apologies, because it was -4 plus a +2, so I get -2 up there. Now compare this vector to the original vector v1. I see that if I can pull out a 2 here, I'm left with -1, 2, 2, which is the vector that we started with. So again, I can replace this matrix multiplication with this scalar multiplication. So in this case, we see that v2 is an eigenvector of A associated with the eigenvalue 2 in this case. And I'm just going to write lambda equal to 2, so I don't have to write eigenvalue another time. So notice that when you have an eigenvector, it's linked to the eigenvalue that you have as well. Okay, so v2 is an eigenvector of A. It's not associated with 1, though. It's associated with 2. So when we have eigenvectors, the different eigenvectors that we have, if they're not scalar multiples of each other, they're typically associated with other eigenvalues. Okay. So just to keep that in mind, that they're linked to their eigenvalues. So we wouldn't say that v2 is associated with 1, because this certainly wasn't just 1 times the vector. All right, so let's do the last one now. -1, 1, 1 for that one. So if I do A times v3, I do 4, 0, 1, -2, 1, 0, and -2, 0, 1, and do by -1, 1, 1 as our vector. So we get -4 plus 1 is -3. We have 2 plus 1 is 3, and 2 plus 1 is 3. And if I notice that I can pull out a 3. So in this case, v3 is an eigenvector of A associated with lambda equal to 3. All right. So hopefully it gives you a little bit of idea of what we mean by eigenvalue and eigenvector. Of course, I gave you the vectors to start with, right? Ordinarily, you're going to be given the matrix and you're going to have to find these vectors. So let's talk about how we find these things. Now remember, eigenvectors need to be non-trivial vectors. So if I want to talk about replacing matrix multiplication with scalar multiplication, we want to find non-trivial solutions of the equation ax equals lambda x. I want to find vectors for x and scalars for lambda, so that I can replace the matrix multiplication a times x with the scalar multiplication lambda times x. So when we're solving this equation, we have to find two things at once, essentially. We have to find both the lambda and the x that satisfy this equation for a given matrix. And we want to make sure we have non-trivial solutions. Certainly, if we put x equal to a 0 vector, we're going to get a solution. But that's not useful for us at all. The trivial solution there is not interesting to us at all. It doesn't help us because I already know how to do multiplication by 0. Okay? Remember, the whole point of this is to try to replace the matrix with the scalar. All right. So I mentioned this a little bit in the other video, but let's just go ahead and work through it again. just solve this like a high school algebra problem. Let's isolate the x, get all our x's on one side. I would like to combine like terms, but currently they're not like. This is a matrix, this is a scalar. To get them to be like terms, I need to put in the identity matrix in here. Now I have matrix and matrix. So I can combine my like terms and get the equation that a minus lambda I times the x is equal to 0. Again, we want this to have non-trivial solutions. If you were thinking about this in high school algebra class again, if this were a number that's not 0, I could divide by it and I would still get x equals 0, right? So to get non-trivial solutions, I don't want to be able to, quote unquote, divide by this matrix. That's not something I want to be able to do, right? So because if I can divide by it, then I can just get a single solution. I get x equal to 0, which is what I don't want. So to get non-zero or get non-trivial solutions, we need that a minus lambda I to be non-invertible or to be singular. Right? Singular means not invertible. If I want non-trivial solutions, if I want an infinite number of solutions here for this x, I need to make sure that I can't do the inverse of this matrix. Okay. And by the way, this is something I should have stated probably back at the beginning. To do eigenvalues and eigenvectors, you have to have square matrices. A has to be square here, otherwise it can't do eigenvalues and eigenvectors. Or at least you can't do them the way we're going to do them. All right, so we have a numeric way to check whether or not a matrix is invertible. And it's invertible if and only if the determinant of the matrix is non-zero. So if this determinant is 0, then I know it's not invertible, and we get infinitely many solutions. That's that whole mega theorem idea thing that we've been talking about all semester. So we want this determinant to be 0, and that's what gives us the characteristic equation. So the characteristic equation of A is setting the determinant equal to 0 and solving that. So the solutions to this equation are the eigenvalues of the matrix. Okay, so the solutions, just to write that down, the solutions to the characteristic equation are the eigenvalues of the matrix. Okay. Now, if you think about how this characteristic equation goes, remember that I is your identity matrix, so it's 1s down the diagonal, 0s everywhere else. Lambda times I will look like you've got a lambda all the way down the diagonal and 0s everywhere else. That's what your lambda times I will look like. So when you do A minus lambda I, just write that over here, A minus lambda I, you're going to get an A11 minus a lambda here, an A22 minus a lambda here, and so on, an ANN minus a lambda here, and then, of course, your other entries in the matrix everywhere else. Not too worried about those. Think about what happens when you take the determinant of this. Well, you're going to get, if you think about just doing expansion by minors here, if I take this first upper left-hand, say you expand along the first row. So in particular, I take this A11 minus lambda and expand. When I do that submatrix, it'll get multiplied by a submatrix that has all of these, and then so on down the line when you do your expansion by minors. When you multiply all this out, the highest power that we're going to get for lambda is going to be a lambda to the n, right? Because the only way I can get a lambda to the end is if I take each of those multiplied by each other, which means I expand along. I get this one times this submatrix, then I get this one times that submatrix, and so on down the line. So if A is an n by n matrix, I get an nth degree polynomial in lambda as I multiply all that out. In particular, I get a polynomial, right? I can't divide. I'm not dividing by any lambdas at any point. I'm not taking a square root of a lambda. I'm not doing an e to a lambda, right? I'm doing positive powers of lambda or a constant. So we refer to this determinant as the characteristic polynomial of A, and it's a polynomial in lambda. So we have P of lambda is equal to the determinant of A minus lambda I. That's the characteristic polynomial. So your eigenvalues are the roots of this polynomial. So the roots of the characteristic polynomial are the eigenvalues. All right. Lots of words. Let's see if we can do a specific example. Okay. Let's go back to our matrix A. We already know that we had eigenvalues of 1, 2, 3 by what we did up in the previous example, but let's see how we would have done this had we just been given this matrix and then asked to find the eigenvalues and eigenvectors. So the first thing you do is I want to do what A minus lambda I. That has the effect of taking lambda and subtracting it off the diagonal. So that's what I'm doing first here, is just taking my lambda and subtracting it off the diagonal. Okay. Now I need to figure out the characteristic polynomial. I need to figure out the determinant of this. So the determinant of A minus lambda I here. I'm going to expand along any row or column, but I'm going to expand along this one because that has a couple of zeros in it. Makes life a little bit easier. The 1 minus lambda here would be a positive 1 minus lambda, because if I do my sign board, it's plus, minus, plus, minus, plus, minus, right? So that's a plus. And then I do the submatrix, so it'll be 4 minus lambda, 1, negative 2, 1 minus lambda. That's an easy determinant to take because it's a 2 by 2. It's 4 minus lambda times 1 minus lambda plus a 2. Oh, hey, I don't know why that's doing that. Sorry. Multiply this part out in the parentheses. You have lambda squared. You've got minus lambda minus 4 lambda gives you minus 5 lambda. Plus 4 plus 2 gives you a plus 6. And lo and behold, that refactors as lambda minus 2 times lambda minus 3. All right, so this is your characteristic polynomial that's factored. Your characteristic polynomial, that P of lambda, is 1 minus lambda times lambda minus 2 times lambda minus 3. We factored it. If you wanted to actually write it out, you could FOIL it, but this is still a polynomial. All right, so we really do get a third degree polynomial for this 3 by 3 matrix. But this is your characteristic polynomial. The characteristic equation would be setting this equal to 0. And we see that lambda is 1, 2, or 3, which is what we found in the previous example. Okay, so we want to talk about how we find the eigenvectors associated with the eigenvalues. We found the eigenvalues, now we want the eigenvectors. So for eigenvectors, we have to solve for each of these individual eigenvalues. So we go back to the original matrix with the minus lambda in it, minus the lambda I, and we plug in the lambda. So it will get 3, 0, 1, negative 2, 0, 0, negative 2, 0, 1. Right? Okay. Oh, no, sorry, negative 2, 0, 0, my bad. Okay, so we want to row reduce this. So let's see how we can do this relatively quickly on our calculator. So I'm going to kick over here. First thing I'm going to do is go to my matrix. Let's edit. I'm going to start with just our original matrix, which was a 3 by 3. And it was 4, 0, and now, of course, I forgot the number. 4, 0, 1, 2, 0, 1, or was it negative 2, 0, 1? It's negative 2, of course it was. Negative 2, 0, 1, and negative 2, I did it backwards. Negative 2, 1, 0, negative 2, 0, 1. This one has the 0 and the 1. This is 0. And this one is a 1. All right, so there's our original matrix. Okay. So I want to show you a couple of tricks where you can use your calculator to help you find eigenvalues without having to necessarily go. I want you to be able to go through the determinant process and factor things, but when you have bigger matrices, sometimes it's harder. When you get third degree, fourth degree, fifth degree polynomials, it gets harder to be able to figure out eigenvalues in particular. So let me show you a little trick about how you can find these relatively quickly. So let's quit out of here. Let's go into your y equals menu here. And now I'm going to go, while I'm in the y equals button, I'm going to do second matrix. I'm going to go to math. And I'm going to hit determinant. And then I'm going to go back to second matrix A and subtract x, because that's the lambda I'm trying to find. So I'm going to solve for x times, go back to matrix, go over to math, and notice number 5 there says identity. That will create the 3 by 3 or whatever size identity matrix you need. If I put identity of 3, that's going to create the 3 by 3 identity matrix. So what I've done here is the determinant of A minus lambda I, which I've done the 3 by 3 I here because A was a 3 by 3. Okay. And now what we're going to do, let me change my window, make this say, well, you know what, I'll zoom standard, and there it graphed it. So here is this is the characteristic polynomial plotted on your screen. And we can see, let me zoom in a little bit. Oops, too far. Well, it's not too bad. Let me change the window here to negative 4 to 4. Now graph it. And as you can see here, the polynomial crosses the x-axis at 1, 2, and 3. So I have a good guess that my eigenvalues are 1, 2, and 3. As a matter of fact, if you go to second calculate and ask it to find a 0 here, let's scroll over. Maybe, there it is. Then just pick a left bound somewhere, go to the left of the 0, pick a right bound, go to the right of the 0, make a guess, and it tells us there is a 0 at 1. And you could do that for the other ones if you weren't 100% convinced that it was 1. There's going to be another check we're going to do here in a minute that guarantees us that the 1 was correct. Okay. But just wanted to show you this really quickly, that you can get these on your calculator, check your work if you're doing these by hand, and see that you really do get the eigenvalues. All right. So we're convinced, hopefully, now that the eigenvalues are 1, 2, and 3. We want to find the associated eigenvectors. Okay, so let's take our matrix A. Ooh, hey, not in here, I don't want to. Let's take our matrix A, and let's subtract off 1 times the identity. I'm going to type it in, even though you don't need to. 1 times the 3 by 3 identity matrix. Whoops. Didn't mean to hit enter. And let's store this in matrix B. This is what we got earlier when I was writing it, when I subtracted 1 off the diagonal. To find the eigenvectors, I want to row reduce this because I'm trying to solve the system a minus lambda I equals 0. So I need to row reduce this like we usually would. So let's do second matrix, and let's do reduced row echelon form, which is B, of matrix B. You could have, I didn't actually have to store it as matrix B. I could have just asked it to row reduce the previous entry, the previous answer. But here is our reduced row echelon form of that matrix. So going back over here, I know it's 1, 0, 0, 0, 0, 1, 0, 0, 0. So that I know that the solutions are, I've got a free variable here in the second component. So the first component would be a 0. The last component would also be a 0, and the second component would be a 1. So I get 0, 1, 0 times the t. So what we see here is that any scalar multiple of 0, 1, 0 is also going to be an eigenvector associated with lambda equals 1. So this is what we refer to as the eigenspace associated with lambda equals 1. So this would be the set of all vectors that look like this, where t is any scalar, or a basis for this eigenspace would just be 0, 1, 0. And if you wanted to write it horizontally rather than vertically, that's okay. But this is exactly that first eigenvector that we, in the example that we did, associated with the eigenvalue lambda equal 1. To do the other ones, we've now got things set up pretty easily to do the rest of them. Second entry, to get back up there. I just need to change the 1 to a 2. Because that was our second eigenvalue. I want to row reduce this matrix. So now do second entry, because I already said we're going to reduce B. And we get that. So going back over, see if I can maybe make this a little bit smaller. So I don't have to keep going back and forth. Maybe. Okay. It's hard to grab this with a pen. At least I find it hard to grab it with a pen. All right, so we've got, for lambda equal to 2, I'll just scroll to the side here. For lambda equal to, the matrix should be 2, 0, 1, negative 2, negative 1, 0, negative 2, 0, negative 1. Because again, remember, we're going back up. Let's see if I can shrink this just a little. Going back up here to this matrix and plugging in lambda equals 2. So 4 minus 2, 1 minus 2, 1 minus 2. That's where this matrix is coming from. Just taking the lambda, plugging it up here. Do the reduced row echelon form. We get 1, 0, 1 half, 0, 1, negative 1, 1, 0, 1 half, 0, 1, negative 1, 0, 0, 0. This is, by the way, what I was mentioning a minute ago, saying that we can check to make sure that we're actually doing this correctly. Remember, the eigenvalues are associated with non-trivial solutions to that system a minus lambda I equals 0. To get non-trivial solutions, we have to have a row of zeros. Every time when you do this row reduction for an eigenvalue, there has to be a row of zeros. If you don't get a row of zeros, you've done something incorrectly. Okay? Always has to be a row of zeros, because we always have to have a pivotless column, and we have a square matrix. If we get a pivotless column to illustrate infinitely many solutions, that means we also have to have a pivotless row. All right, so there always, when you do this row reduction, has to be a row of zeros without fail. All right, so now we can see what the solutions are. Free variable is the third one. Move that over, I get a 1. Move that over, I get a negative 1/2. Now it looks a little bit different than the eigenvector that we had above before, right? If I go back all the way to the top here, maybe I get it to scroll correctly. We had negative 1, 2, 2, and right now we had negative 1/2, 1, 1. But remember that when we solved this, t can be any constant. In particular, I can take a multiple of this and multiply by 2, and I still get the same thing. So this would be the same thing as a t times negative 1, 2, 2. Because remember, t is allowed to be absolutely anything. Okay? It's like an arbitrary constant when you do an integral in calculus. If I take 2 out of it and stick it in the matrix, it's still an arbitrary constant here. It doesn't matter. Okay? So the basis for the eigenspace here, associated with the lambda equals 2, will just be the vector negative 1, 2, 2. And the other vector would work too. The negative 1, 1, negative 1/2, 1, 1 also works. All right, last one. We do second entry, and change the constant to a 3. And then second entry, and row reduce. So changing this to a 3, put it in the 3 for lambda, and then we row reduce to get this matrix. So putting in the 3 for lambda equals 3, we got, it should be 1, 0, 1, negative 2, negative 2, 0, negative 2, 0, negative 2. And then when you row reduced it, if I remember correctly, it was 1, 0, 1, 0, 1, negative 1, 0, 0, 0. Yep. Okay. So this again says the third one can be anything. The second one has to equal the third one. And the first one, oops, it's a times, not an equal. The third one could be anything. Third component can be anything. The second one has to equal the third component, and then the first component's the negative of the third. And again, this is what we saw as our eigenvector in the very first example. So a basis for the eigenspace here associated with lambda equals 3 is going to be the vector negative 1, 1, 1. So that's the process we go through to find these eigenvalues and eigenvectors. Okay? All right. So let's talk a little bit about some additional properties. Say you have a triangular matrix to start with. Remember, triangular means that it could be upper triangular, so everything below the main diagonal is 0. It could be lower triangular, so everything above the main diagonal is 0. Or it could be diagonal, so everything above and below is 0. But think about how you do the determinant. Say you had an upper triangular matrix. Oops, this should be a 3. And everything down here is a 0, and it doesn't really matter what's here. When we do the determinant of this, remember, it's just the product of the diagonal. Okay? Remember, when we do the determinant of a triangular matrix, it's just going down the diagonal gives you the determinant. So if you want eigenvalues of A, if I erase this now, if I had a minus lambda, minus lambda, minus lambda, minus lambda, the determinant is just going to be A11 minus lambda, A22 minus lambda, ANN minus lambda. Right? That's going to be our diagonal. If I have a triangular matrix, remember when we solve for eigenvalues, we just subtract lambda off the diagonal and take the determinant. If it's triangular, I take the determinant just by doing the product down the diagonal. So this is our characteristic polynomial, But that's easy. It's already factored for us. So I know that the eigenvalues then are just the diagonal entries. Okay. So in general, for a triangular matrix, the eigenvalues are the diagonal entries. Okay. Pretty straightforward. It's not bad if you have a triangular one. Now, of course, we don't always have triangular matrices, but if you do, you have a nice way of being able to calculate the eigenvalues. All right. So let's talk about what happens if you have a square matrix and it's invertible. Okay. Well, let's think about it. I know that it's invertible if and only if the determinant of A is not 0. Okay. Well, let's go back over to how we calculate eigenvalues. We would set this equal to 0, right? What would happen if lambda were equal to 0? If lambda equals 0 as an eigenvalue, what happens? Well, if lambda equals 0 as an eigenvalue, then I would have determinant of A equals 0, which would mean that A is not invertible, right? So if A is invertible, I know that the determinant's not 0. If the determinant of A is not 0, then lambda cannot be 0 for an eigenvalue. And vice versa, if lambda were equal to 0, then the determinant of A is equal to 0, so then A wouldn't be invertible. So this is if and only if, over here, lambda equal to 0 is not an eigenvalue of A. So by the way, this gives you another condition for whether or not a matrix is invertible. It's invertible if and only if lambda equal to 0 is not an eigenvalue. All right. Let's look at this particular property, and there's other ones that go along with this. But let's look at this particular property. If lambda is an eigenvalue of A associated with an associated eigenvector V, then what about lambda to the k? All right, well, if I have A times V is equal to lambda V, this is eigenvalue of A with associated eigenvector V. I want to try to do lambda to the k. Well, let's do lambda squared first. Let's not be crazy. Let's do lambda squared first. All right, so let's multiply both sides by A. So then on the left-hand side, I get A squared V. On the right-hand side, I can move this constant out in front. So I would have lambda times AV. But I already know that AV is the same thing as lambda V. So I would get lambda squared V. So let's look at this equation. A squared V equals lambda squared V. V is an eigenvector for lambda. So V is automatically non-zero. So I have a non-zero vector that I can replace the matrix multiplication with the scalar multiplication. So this tells us that V is an eigenvector for A squared associated with lambda squared. No doubt at all. Okay? So in particular, I know that lambda squared is an eigenvalue for A squared, and the eigenspaces don't change. Right? The same vector works for lambda as lambda squared. Notice there was nothing special about squared here. I could do a cubed. I would get the same result. I could do a fourth power or what have you. So this says that lambda to the k is an eigenvalue for A to the k with associated eigenvector still lambda, or still v. The v doesn't change as we exponentiate. Same eigenvectors. The eigenvalues change by the same power. By the way, if A is invertible, this still works, because if I had an A inverse over here, lambda we know is non-zero, so then I could just rewrite the equation. So this works for negative exponents as well. And the v still doesn't change. Okay? All right, so anytime you do a power, whether it's a positive or a negative power of A, we still get the same eigenvalue raised to that same power, and then the eigenvectors stay the same. All right, let's see if we can do a bigger example here. Let's look at this A. See if I can type this in my calculator real quick. Let's go second matrix, edit A, and I want a 4 by 4, 3, 1, negative 4, 0, negative 18, negative 8, 24, 0, negative 4, negative 2, 6, 0, 15, 8, negative 20, and negative 1. All right, so first things first, let's find some eigenvalues. Well, notice that we already have up here, whoops, not stat plot. We already have up here that we've got our determinant of A minus X times the identity matrix. We already had that typed in, except in this case, the A is a 4 by 4. Remember, this generates an identity matrix, but you have to specify the dimension. So I do need to go over here. Oops. And change this to a 4. And now graph it. All right, cool. So this one looks like our eigenvalues must be negative 2, negative 1, 1, and 2. Okay. We could have gone through and done the determinant by hand and factored it by hand and all that good stuff, but the calculator here helps us figure out where those eigenvalues probably should be. All right, let's see if that works. Let's go back and grab that previous entry stuff. I think that negative 2 is an eigenvalue. So I'm going to put negative 2. So I did A minus negative 2 times the identity matrix on 4, the 4 by 4 identity. Let's store it in B. And then let's row reduce B. Cool. And if we want, we can make those fractions probably. There we go. So here is our reduced row echelon form for that particular matrix. So going back over here, with the calculator, we got lambda is negative 2, negative 1, 1, and 2. For lambda equal to negative 2, the matrix would be just 5, 1, negative 4, 0, negative 18, negative 6, 24, 0, negative 4, negative 2, 8, 0, and 15, 8, negative 20, and 1. When we did the reduced row echelon form, that first row was 1, 0, 0, 0. The second row was 0, 1, 0. I believe it was the third. 0, 0, 1, 1 12th, and 0, 0, 0, 0. Again, we see that row of zeros here. See that row of zeros? That's a good thing. We want a row of zeros because we want infinitely many solutions. So we get, for our eigenspace, this last vector can be anything, or the last component can be anything. This one will be a negative a 12th. This one would be a negative a third, and the top one would be 0. If you don't like fractions, multiply everything by 12. It doesn't matter. You can leave it like it is, so your basis for your eigenspace here associated with lambda equals -2 will be the 0, -1/3, -1/12, 1. And then you can go through and do the same thing for the others. So let's do one more. I'll leave the other two for you for practice. Let's say I want to do the one for 1. So let's do second entry, second entry, second entry. I want to change that -2 to a 1. Like I said, I'm going to leave the other two for you to practice. There's our matrix. Second entry, second entry, second entry. There's our B. A little bit nicer here. So 1, 0, 0, 2, and so on down the line. So for lambda equal 1, the matrix with a reduced row echelon form is 1, 0, 0, 2, 0, 1, 0. Is it -4? Yeah. 0, 0, 1, 0, 0, 0, 0, 0. So then our T will be times, well, the last component can be anything. The third component is 0. The second component has to be 4, and the first component has to be -2. That's our null space, right? We're trying to get that equals 0. We're just doing the null space computation there. Solving the homogeneous system. This is stuff we've done. So then your basis for your eigenspace now, associated with the lambda equals 1, will be -2, 4, 0, 1. And then you would have two more to do for the other two eigenvalues. So again, I left these two for you to practice with your calculator. And again, feel free to ask me a question if you need to. All right, so last thing here, let's go back to the mega theorem. We haven't been visited that for a while. I can't even remember what the last entry was in our mega theorem, but we got a few that are missing. I think we may need to be able to do the row space and the column space ones, but that's okay. If you look at your book on page 366, this should give us the complete list of everything that we've done so far. I think I did rank and nullity, but I didn't talk about orthogonal complement. The only ones that are on page 366 that we haven't done are H and I, and that we'll talk about that when we get to chapter 8. But, so we also have then that if I want to talk about the orthogonal complement now, so another equivalent condition to being invertible. I don't even remember what letter we're on. I'll let you fill in the letter. We have the orthogonal complement of the null space of A is all of Rn, because we know that the nullity had to be 0, so that means the null space is empty, so its orthogonal complement is everything. For the next one, the orthogonal complement of the row space of A is simply the 0 vector. To go along with our least squares, I didn't talk about it after least squares, we get that A transpose A is invertible. And then what we just talked about today, we would have that lambda equals 0 is not an eigenvalue of A. So we got a few more equivalent conditions that popped up. We would be at U, I believe, if we had done the linear transformation stuff back in chapter 4, which I'm going to talk about in chapter 8 when we get there. So if I'm right then this should be SRQP, I believe, is where we are. I don't know. You'll figure it out when you add it to your stuff. So anyway, that's section 7.1. Hopefully I'll get internet issues figured out, but I'm not making any promises for Wednesday. I will keep you posted. If things work better, we'll try to Zoom, but otherwise we may just have to do this asynchronous stuff for the rest of the semester. I don't really want to do that, but that just may be what we have to do. So anyway, I'm going to post a homework assignment on Moodle today as well over the stuff in chapter 7 that we're doing, plus the last stuff that we just did with Graham Schmidt and least squares. But that won't be due until a week from Wednesday, so that'll be due on the 29th. But I'll get that posted today as well. So anyway, I will talk to you all later.